ti nejde do toho streamu?
Ne.
Ne?
No, samozřejmě, že jde, ale jako jde to tam, já to rozpojuju až potom.
Jo, no,
Haló.
aby to mohlo slyšet.
Dáme buzz boost. Haló. Haló. Haló, no.
Tu máme ještě ty.
Co? Jo, ty samolepky. Super. Test, raz, dva, tři. Test, raz, dva, tři. Raz, dva, tři, raz, dva, tři. stačí.
So, hello, guys. Can you please take your seats? We will start in 2 minutes. So. It's a bomb, yeah. No. So, hi. I'd like to welcome you on the next Cloud Native Prague Meetup. This time the topic is the stateful of the Kubernetes, so we will speak about the storage, mainly about it. So, we are both, which are organizing these events, me and Pavel. First of all, I'd like to say that it's free of charge. We don't get any money from it. Yeah. Cloud Native Prague meetups are Cloud Native Computing Foundation events. These events happens in most of the countries and also big cities. So we are making just in the Prague. I think we are only one event in Czech Republic right now. There's the second one is in Bratislava. So what is Cloud Native Computing Foundation? I hope that most of us know about it. But the CNCF is just a foundation. It's a project of the Linux Foundation, which tries to help open source project to grow, like finding the contributors and also spreading the knowledge about the tools, and also try to help companies to understand how to make the platform or the tools based on these open source. So, I'd like to say also something about our community. We have the website cloudnativeprague.cz where you can subscribe and you will see the upcoming events. We also have Slack where you can reach us. I mean, not only us as the organizers, but also when you can reach our community members, so you can use the Slack. We also store slides from these meetups on the GitHub. And also we are recording these events and publish it to the YouTube channel. So you can also check it. And also if you wanted to help us, I mean providing the space, speak at the events, or even if you'd like to help us with organizing these events. So we have involvement.cloudnativeprague.cz and you can reach us and we will welcome you with helping us with this. But as I said, it's just before any payment. So. I'd like to mention that we are not only one community in our location. As I said, there's the Cloud Native community in Bratislava. There's also Python community, DevOps meetups and DevOps days, and also Golang meetups. I prefer the Golang ones because I really like it. And also we have Láďa, is the founder of the Golang meetups. And also we, with the Bratislava community, organizing the conference. It's called KCD. It will happen next week, so I will speak about it later. So I'd like to thank Keboola because they provided us this amazing space and also the refreshment. So can you please make some applause for Keboola? So, something about the KCD. KCD is Kubernetes Community Days. It's just a shortcut of it. If you are still not signed there, so you can use this QR code or just the discount code. It's for 30% discount. As I said, it happens next Thursday and Friday. It's just a 2-day conference. It's also streamed. So if you can't attend it in person, so you can still watch the stream. So, okay. And something about today. So we have two speakers. Both of them are Ondřej. So first is the Ondřej Hlaváček from the Keboola. So. He will be speaking from my point of view, very interesting topic about so many stateful jobs running in the Kubernetes. I have never seen it, this workload running in the Kubernetes, so it's pretty cool. And also there is the second speaker, Ondřej Smula. So can you please also make some applause for them? And he will be speaking about the storage options in the Kubernetes. So if you wanted to run it, your own Kubernetes, not in the cloud, so maybe you will be interested because this is the biggest painful thing when you are running on-premise Kubernetes, I mean, managing the storage. Of course. But if you wanted to think about open source, so he will be speaking about the solutions, yeah, of course. So, if you have any question, we have Slido, so please use it because we will read the questions there. Of course, you can ask here, but we prefer the Slido. So, you can just copy the QR code or just type there, open the Slido and type there CNP. So, I think nobody is scanning it, so we can finish it. I don't want it to speak more. So thank you, and I'd like to welcome the first speaker and enjoy it. And before we start, sorry, sorry for that. There is the beer. I mean, the tab there. If you wanted to go to the toilet, so you will have to go down to the stairs and turn right. And also, if you wanted to take some stickers, so there's the table. I mean, near to the door, so you can take it. It's for free. So enjoy it, and thank you, and welcome the first speaker, Ondřej.
Mic check, mic check. Everything okay? Awesome. Nice and beautiful. Do you have the clicky thing, please? Somewhere? Oh, it's up here. Yeah, I'm working on it. So my picture's ready. How's it looking up there? Awesome. So thanks everyone for coming. Welcome to our offices. This is a really nice place to see all of you guys. We are doing quite a lot of meetups here. The space is suited for that, so I'm really happy to start our first Cloud Native Prague meetup here. I want to apologize. I made a huge mistake in the title of my presentation. We are not running 10,000 jobs daily. We are running 10,000 jobs each hour. So sorry for that. The scale is a little bit bigger than that. The title or the subtitle, running 10,000 ephemeral stateful jobs in managed Kubernetes each hour, is quite long, but we'll go through each part, each word of that in the presentation, and you'll see what does it mean. By the way, we're hiring. We're currently hiring for 19. We have 19 open positions. 5 of that is for engineering. It's developers in multiple languages. Also, you can join my team as a cloud or infrastructure engineer. So, was that mine? I'm sorry. I'll mute that. So that's add windows done. Something quickly about me. Outside of work, I really like to be outdoors. I have 2 small kids. I've been in Keboola for 15 or more years. I don't even remember when I started here, but the journey was quite fun, exciting, and it's changing quite a lot. The company is growing. I changed places quite sometimes. I started in Prague, then let's say 12 years, 13 years ago, I moved to Vancouver to help one of our co-founders start our North American venture. I stayed there for 3 years. Then I moved to Indonesia and helped our Singapore office there, and then back to Prague, and now I'm in Liberec because I like being outside. I started in Keboola as a backend engineer. I went through front end, back and forth, full stack, and now I'm doing infrastructure and SRE especially. Here's my email. I am not very active on Twitter, X, or LinkedIn, so if you want to reach out to me, have any questions, get me here, or here's my email. So I'll give you a short introduction about what Keboola is, what we do, and then I'll just go a little bit deeper. We sell ourselves as a self-service data operations platform. What does it mean, self-service? Is that end users can go, and by end users, I don't mean technical people like developers, but business end users like analysts or CEOs and all those people can go into the platform, do their work. They don't need to know any SQL, Python, or anything, and start working with the data they have in the platform. Data operations platform. I'm sorry. Was that you? Okay. Data operations platform means that it's for everything you can do with data. You can start organizing your data as a small company, then as you grow, the platform grows with you, and it's ready for small companies and for large enterprises. Was that you again? We currently run on the 3 major clouds, AWS, GCP, and Azure. We offer our platform as a public multi-tenant solution in all those 3 clouds, and also as a private single-tenant solution. That means that we install into your VPC, into your cloud. We have around 15 installations of the platform. They are almost all the same, the exact same installation. It only depends which cloud, which region, if it's private or public. We try to use as many managed services as possible because our engineering team was, let's say, 13 people a year ago. Now it's around 30. So we're growing, but we were small and we want to focus on the core business, which is working with data, not managing Kubernetes or metadata stores, databases, and so on. So we are buying as many services as possible from the cloud vendors. So of course we use managed Kubernetes. We use managed metadata stores. That's a fancy name for a MySQL database. and we use and manage warehouses. The situation with warehouses is we support many warehouses that the client can plug in under the product or under the platform, but we mainly focus on working with Snowflake because of its performance and flexibility. Currently, we are also working with BigQuery, so you can plug in your BigQuery data or your BigQuery warehouse or subscription under the platform. And also you can use Redshift if you're on AWS or Synapse if you're on Azure, and we support a couple more warehouses. So basically you bring, we either provide you with the managed warehouse or you bring your own warehouse under the platform. So the title was about jobs. What is a job? It's a super busy slide, don't worry, we'll go slowly through it. A job. We're on a cloud-native meetup, so you may think it is a job in Kubernetes, but technically it's not. It's something different that evolved from something we started even before Kubernetes was launched or developed. It's an arbitrary container. Arbitrary means that you, as an end user, can bring your own container or image that we run and execute on the platform for you. So you may look at it as serverless, sort of. It can actually be multiple containers, because you can have a really obscure data source like FTP, where your data lives and you want to extract that and bring into the platform for other users to use. And the data is gzipped with a password, and your CSV file does not have a header. So instead of implementing all that into one single container, because you need to re-implement it for all other your bizarre data sources, you can run a sequence. You can see it as a Linux pipeline. You can run a sequence of containers, and each has a very simple job. Your FTP extractor or data source has just a single purpose: download the data from the data source and let it be. And then comes another container that can do CSV manipulation, decompressing, and so on and so on. So it just the one job can be a series of containers that run in sequence. And it's not serverless. I don't really remember why I put it there, but for serverless, you may imagine that it runs, oh, I know why. Because the container you bring there can be anything you can build into an image. It's not like in serverless, you usually bring in just the code, and you have a pre-built image with JavaScript or Python. Here, you can bring your own image with everything you need for the job you want to do. So it's your container, your image, and we run it. Each job has an end-user configuration. So you can have the same image, can be executed multiple times with different configurations, different FTP servers, different passwords, and so on. And they can run cron lines scheduled. So you can say, okay, every midnight I want to download data from those 3 FTP sources. Or it can be a one-off, just need to download the data just once. We allow for up to 24 hours runtime. That means that your FTP extractor can run 24 hours if you have a really slow connection to your on-prem FTP, or you have large file you want to download. We allow for arbitrary memory and CPU requests limits, or CPU and memory resource allocation. So for some jobs you want less memory or less CPU than other jobs. Of course, you pay for the memory and CPU that you use. From our experience, those jobs are more I/O and network heavy than CPU, because it's downloading data from somewhere. But the gap is closing. We are seeing more complicated or more CPU heavy data operations like machine learning, AI. So you can actually build an ML model within the platform. And that job is not really I/O heavy, it's more CPU heavy because it needs to compute a lot of things. So some of the workload is more I/O and network, some of the jobs are more CPU and memory. These jobs cannot be resumed or paused. If you're downloading a single CSV file from an FTP, you can resume, but it's some other weird data source. You can't pause it. You need to download it or delete it and start from scratch. So that's one thing that is quite important and goes through the whole presentation. It depends. The data sources in general do not support pausing and resuming. It's either if you're downloading from let's say, Salesforce, you would need to figure out which record are you downloading. But if you use a bulk downloader, then it's really complicated to keep track which record is downloaded. Or there's an external state, you just don't know. You don't get the information where you stopped it during the download. So the process or the approach is called micro batches. It's not streaming. We're not getting the data and immediately processing it through the pipeline. It gets downloaded on the disk, and then other process or other container of your job can start on that. So we are running, as I said, around 10,000 jobs an hour. It's during peak time. Daily, it is 200,000 jobs, all clouds and all installations combined. Altogether, they take the runtime during one single day is 18 months. So all the jobs they run, if you put them in a sequence, they would run 18 months. It's quite interesting. There's very little. The first graph on the right side. There's very little daily seasonality. This is a snapshot of a week. Of course, Sunday is the slowest, but it's not that significant decrease because clients usually want to pre-compute their reports on Sunday and have them ready on Monday. So there's no dip. Like the weekly seasonality is almost nothing, almost none. The daily seasonality, that's the middle graph. That's quite interesting, but I can't really see that. This is a snapshot of a whole week. I can't see any trend there, so it's sort of random. The lowest point is 5,000 jobs an hour. The high points are around 10,000 jobs an hour. It doesn't really, I don't think there's a seasonality. Just to me, it looks really random. And the table, that is also interesting, is how many jobs take certain time. So during that 200,000 jobs a day, almost half of that, which is 100,000 jobs, take less than a minute a day either. Just quickly connect to data source, pull the data, ideally incrementally. They don't download the full data set, only what is new from the last job. The jobs can run every 5 minutes, every 15 minutes, so they just grab the increments, the additions, and store them in the warehouse or process it. But altogether, they don't take that much time. It's 48,000 minutes. And then there are other buckets. Interesting is that the jobs that take more than 6 hours. During that week I snapshotted, there are only 61 jobs taking more than 6 hours. The limit is 24 hours. But they took altogether almost roughly the same amount of time as the jobs less than 1 minute. 33,000 minutes. It's not seconds, it's minutes. It's like seconds divided by 60. So I think we are running quite a nice scale. I didn't know the exact numbers until I started the presentation, so I was really surprised. And there are some benefits to it. It's like the seasonality. If we were running just in Central Europe region, there would be a significantly more seasonality in the data. But running it globally on this scale, there's no seasonality. Some issues, they just smooth themselves out. They stop existing, but it brings some new and interesting problems and issues. And that's what I want to talk about today. How it all started. I'm the old guy in the company, but I'm not the only one. There are lots of guys that are with the companies as long as me. We, in 2015, I think it was, we were thinking about, okay, we want to bring the customer operations or the customer code inside the platform. So we started thinking, okay, how can we run arbitrary code? The serverless was a non-existing term, so containers, Docker was quite young, Kubernetes didn't even start then yet, so we didn't know what to do, so Docker was the way to go. So we built our own containerized job orchestrator. What it did was basically orchestrate the containers using Docker. At that time, we were only on one cloud, and we had only one instance. So on that, or one instance, I mean one installation of the applications. So we started very simple approach, running all those containers on a single node with a large disk. I think it was 1 terabyte in RAID 0, so to double the speed. And it worked good for quite some time. There was no auto-scaling. when we figured out, okay, these jobs are getting too slow and the instance is too heavy or it has some issues, so we started another node. So, or increase the disk size if we need more I/O operations, because as I said, the jobs are more towards I/O and network heavy. So there were manual scaling. Docker at that time did not have any memory and CPU requests, only memory limits and CPU shares. And CPU limits, I think, were not invented at that time yet, so that was CPU shares. So we somehow set it up. And the benefit of that, there was no scheduling. Everything ran on the number of nodes that we provided for this orchestrator. We also introduced a very simple interface between the platform and your container. Basically, it is a configuration file you get on a disk in a mount, and then you serve us the data in a CSV file somewhere else on the disk. And it's super simple. There was no API, everything was just on the disk. This was super simple, but it was very cost effective, and the performance was quite good at that time. But as things age, this needed to go. We had a good share of low-level I/O issues because all the containers were using the shared disk. So we were dealing with caching on the disk and VM dirty bytes and all that stuff. We had to figure them out. Also, we couldn't offer memory and CPU guarantees to our customers. So we could not guarantee the speed and that they're running, or the speed of their processes. The scalability started to be an issue because it was manual, so we were scaled to serve the peak. So we have to observe regularly what are the peaks and scale the infrastructure for that. Observability at that time was non-existent. You had to go on the node and start poking in Docker. Sorry, slide back. It had very limited networking options. Basically, all we could do is put their network none or network bridge, so we could not limit where the containers has network access. And we started to build years of experience and product features into that container orchestrator. And also, this was built on top of ECS. It was Elastic Container Service in AWS. And at the time, there was no generic alternative in other clouds. So at one day, we figured out we need to start our operations or our platform in other clouds. The rest of the platform, other services and APIs, we migrated them to Kubernetes. But still, this container orchestrator, was the last to go. So we figured out, okay, now I believe it was 5 years ago, something like that, 4 years ago, I don't remember correctly. So we figured out, okay, we need something generic. We have already Kubernetes for all the other services. Let's try running this in Kubernetes. What would be the ideal case? What would be the ideal implementation? So we would have operators there to handle the job lifecycle. We would have CRDs for everything, maybe even for replacing some of our APIs, using the CRDs as a metadata store for the platform, even for the user config and cron jobs and all the things that users can do in the platform. We could leverage the Kubernetes APIs to store that. We could have dynamic volumes, allocate a large or small disk, fast or slow to certain jobs, and ideally it would be stateless, and we could move the workload to other nodes when required. That would be awesome if this could work. So why this hasn't happened yet? The code base. There's lots of time in the code base that we put in there, lots of product features and bug fixes and edge cases that are not 100% compatible with this approach I previously showed. Mostly one of them is the statefulness of the workload. We have around 1,000 images from our end users that they use daily to process their data, and they are used to store the data on the mount, so we can't easily switch there. Then also we were not sure if the features on Kubernetes are ready for that kind of workload. I mean, even volume and the features that we need. And also we were not sure about the price The price is a really interesting topic. I'll talk about that later. So but we explored that path, and we are still exploring it today, and we are moving slowly towards a better implementation in Kubernetes. So what are the key problems that we are facing? I explained to you that we are running multiple containers in a sequence. That is not natively possible in Kubernetes. You can run multiple pods, but they can be scheduled on different nodes, so you would need a per-second volume, which is expensive, that is slow. It can be fast, but it's expensive. You cannot provision too many volumes at the same time. I think we hit multiple limits on AWS. If it's a network disk, then you can only attach 8 disks to a node. If it's a block device, I think we hit a limit of 50. I don't remember exactly, but within an hour you can only add 50 disks, so you would need to introduce some pooling, but you cannot attach 2 jobs to the same disk because it's read-write once. So there's lots of issues, and this is all bringing the price up. And for the scale, again, it's 10,000 jobs each hour. It didn't really work for us. We would need either to throw a lot of money at it, which is not business, like it's not feasible from the business point of view, or we would need to figure out a different solution. Also, we learned by our mistakes that garbage collection of the resources on Kubernetes, CRDs and so on, and the number of resources is quite important even on managed Kubernetes. In AWS, we managed to shut down the control plane twice. Both it was the same bug 2 times. We couldn't learn from our mistakes. We had around 400,000 secrets on the control plane, and the API just stopped responding. We had a call with the engineers, they fixed it, and then a couple days later, again, 200,000 jobs daily, so the 400,000 limit, you get there very quickly. So a couple days or a couple weeks later, we were there again. And when you have 400,000 secrets in Kubernetes control plane, there's almost no easy way how to delete them. Like the kubectl cannot list it. And the same applies to all the resources that are in Kubernetes. We were just not sure if we introduce a bug and we forget garbage collecting the resources, if the platform will survive. Has anyone here tried listing pods in Kubernetes clusters when you have more than 1,000 jobs or 1,000 pods there? Is it fast or is it slow? It's super slow. Sorry? Yeah. So there's and we have 10,000 jobs every hour that will be there. We can garbage collect them, but you will need to garbage collect them very often. So we are quite hesitant, and we are observing and slowly figuring out the way. And also, the other issue is latency, or like creating the resources in Kubernetes that introduces very slight and very small latency. But in this scale, we are working at every second counts. If you delay 1,000 jobs of a customer by a second, it's 15 minutes. It can be really difficult for them to cope with. So what we did and how we implemented it, there are 2 reasons for that. We were not that skilled in Kubernetes at that time when we were starting building that, and also we were not sure if it can handle what we need. So it still runs in Kubernetes, but the Kubernetes is there just to serve one purpose, to run pods, and that's it, nothing else. All other features of that, we deal with them by ourselves. In that pod, there are still parts of the original orchestrator 10 years old now, and that code is not fully Kubernetes compatible, so there's some tweaking and some really weird stuff going on. But we use Kubernetes to run the containers. There is no replication controller, so it's just a single plain pod, nothing is around it. The pod is created, scheduled, executed, then it's deleted, goes away, and we collect the logs. Our application, or our series of services and applications around that, they behave somehow like an operator, but it's custom built, there are no CRDs, all the configurations are within the platform that we use. They are not within Kubernetes, it's in the platform, and all those services just take the configurations from the platform, start a pod, in Kubernetes, wait until it finishes, collects the logs, and deletes it. That application is spread into multiple applications. There's one called Job Runner, which is basically the container execution wrapper, which is basically that old orchestrator that runs just a single container or a single job. And there's the job queue daemon, which is something like an operator, which schedules or puts the resource or puts the resources on the Kubernetes cluster and monitors what's going on there. Scheduler has the cron stuff that allows us to run the jobs in a certain time, and public and internal APIs to communicate the status of the jobs. So basically everything that Kubernetes has and does, we have somewhere else that is built for the scale and features that we have. Important thing is that still all containers of a job, remind you, the job can be multiple containers because it can have multiple operations inside. They are co-located and they are on the same node using that disk mounted attached to the node. But even with those limits, we can have auto-scaling, which works really wonderfully. So if there's a lot of new jobs coming in, Kubernetes starts a new node, and you can start scheduling those jobs on the new nodes. So that gets rid of many issues, for example, with the I/O operations that we had in the past. So what are the issues of that solution? The first issue we had was that it was still too expensive. Before, we had 4 nodes, let's say 4 nodes on one installation that was running all the workload. Now with auto-scaling, the workload can spin up 20 nodes. So it started to be very expensive. How did we deal with that? We had 2 approaches to that. One is that we didn't go with the best practices, Kubernetes best practices, and the requests are 90% less than the memory and CPU limits on Kubernetes, because the workload is typically I/O heavy, so memory and CPU, it's of no interest to us. And also, if there's some, in most cases, now I'm speaking in large volume of jobs, so there are exceptions, but in most cases, let's say the FTP extractor, there's some CPU and memory peak, but it's very short, and the rest is just network. Download data, and then some CPU and memory. So we can use very small requests compared to the limits, and that works for us. For the workload we have experience with that, we know how the workload works, so we can just throw away the Kubernetes best practices and create requests that are significantly smaller than the limits. Then another approach that we did this didn't do everything for us. This didn't bring the cost down to the level that we wanted. The other approach we did, we looked at the table. It's the same table again. How much time do these jobs take? What can we do with it, and how it works with auto-scaling? Imagine you have a new node, so you scale up certain jobs on the node, and then the autoscaler looks at the node and figures out, okay, there's less than 50% request, then this node has memory and CPU, so let's schedule it for a scale down. So in ideal scenario, all the pods will be evicted, and the node will scale down in a short time. But in our case, the jobs cannot be evicted. They need to stay there, they need to finish their job. And if the job takes 6 hours, the node is scheduled for scale down, but it still runs for 6 hours. And you cannot schedule no other pod on the node. It stays there, the job can have 1 gig memory and 1 CPU memory limit, but the node is still there, it's running, and you cannot utilize it. So we looked at the data, as a data company of course, and we figured out, okay, what can we do? This graph, the lower graph, is number of nodes. So I'll explain what we did. We figured out we can schedule, where we can separate or bucket these jobs into, we did 3 groups. There was one group, let's look at the jobs that take less than a minute, then something between 1 and 15 minutes, there's another significant portion, and then jobs that take longer than 15 minutes. And we decided, okay, it might be a good idea to start scheduling those jobs together. So all the short jobs are scheduled on a separate node pool, a separate set of nodes that scale up and down automatically. And then the 1 to 15 minute jobs, they are scheduled on a separate node set, node pool, or whatever it's called in your cloud vendor. And the rest of the jobs that take longer than 15 minutes are scheduled on a completely different set of nodes. That actually work wonders. So this is the graph shows how many nodes. The dark blue line shows how many nodes are there for the short running jobs. You can see there's a really significant peak in the middle. It scales up to 20 nodes for 15 minutes. That's the midnight. It's like May 26th, it's just midnight. Everyone wants to start scheduling their jobs at midnight. That's just the society goes. Midnight is a good time to schedule my job. And the jobs, majority of them take less than a minute. So this scales up to 20 nodes. And then they disappear, and you can scale them down because they all disappear from the nodes. But the light blue line are number of nodes for jobs running more than 15 minutes. You can see it's almost constant. So there is a significant workload that is constant, and you can have a separate node pool for it and schedule them on the nodes that are supposed to run those long running jobs. So this helped us. I'll repeat what happens if we didn't do that. If you scale up a new node because you have an incoming workload, and you schedule a long running job with a short running job on the same node, and then the short running job disappears, autoscaler says, okay, this node is almost empty, there's only one pod, so please evict, drain, and delete the node. But our workload cannot be easily evicted or moved somewhere else, it needs to stay there. So that node would stay there until that one single job that is not using the node, not using the node ideally, we would wait until that job is done and pay for it. So these two approaches, they allowed us to bring the costs down back to a similar level to the stuff, or to the approach, or to the approach we had before. Then we have another issue that we didn't solve yet, but we know how to do it, but we haven't had time to do that yet. And it's the scale up. You can see when you are scaling up from 5 to 20 nodes, each node takes some time. It varies from cloud to cloud. On AWS and GCP, the scale up, just the node takes 1 or 2 minutes. On Azure, it takes 7 minutes. Then you have an empty node, and you need to pull all the images you need there. And that can take some of the images that we run. They have multiple gigabytes. So if you have a Python image with multiple libraries, you download 2 gigs, then you decompress it, it's 8 gigs. It can take another 5 to 6 minutes. So you just wait 15 minutes until the node is ready and can run your workload. So there are two solutions that we are aware of, and that we are sort of implementing the first one. It's the node warm-up. You have a fixed number of nodes running all the time. So basically you are getting rid of the autoscaler, but for the benefit of speeder or faster job start. And also recently we figured out that we can also decrease the time to download the image from the registry if you have some local registry cache. So that would bring down the time to download the huge image or huge number of images that needs to be downloaded on that node. So we have that approach, and we are still evolving that approach. Why? Because it's still tailor-made. There's lots of internal knowledge and internal experience built in that, and we are looking into giving the whole platform to someone else to install and operate. Imagine you have your own on-prem cluster, so you could install our platform there and run it by yourself. It's not ready yet, but this is somewhere we're heading, and that needs improving and being, if everything runs as ideally in Kubernetes as possible, there's lots of people that can understand it, that can observe that, monitor, and fix issues. If it's a house-made solution, it won't work that way. We wouldn't be able to scale. What are we fixing? We want to finally replace the original orchestrator started 10 years ago. There are still lots of code in that. that needs to be replaced in order to be Kubernetes, we call it Kubernetes native. And also we are thinking if there's a way we can start being stateless, because being able to move the data or move the process to a different node is quite good. It can bring the cost down because you can just, you can swap, you can move the workload to another node on the fly. That would be really nice, but it would be a complete paradigm shift for us, for the platform. But it's something worth exploring because the tools evolve. It might be good in the future. So that's the end of my presentation. Thank you for your time. Do you have any questions? I believe you get the mic.
We have question on Slido, so we will start with them and then we will move through here. So give me a second. Just open it. Just closed, unfortunately. So, what are you using as the broker for these long-running jobs? I mean, async jobs. RabbitMQ, or?
Oh, it's a good question. Currently, we use what the cloud vendor has there. We are looking into adopting RabbitMQ or a similar solution, but it's SQS on AWS Service Bus in Azure and pops up on GCP. So it's a managed service, but moving forward, we want to have something that runs in Kubernetes, because it's less services to manage in the end.
Okay, thanks. So second question is, have you investigated, considered projects such as kcp.io, for managing some of the resources such as CRDs separately from the Kubernetes cluster itself?
Can you repeat the question, please, or can I see it? Have you investigated or considered projects such as KCP for managing some of the resources separately from Kubernetes? No. Actually, to be honest, this is the first time I've heard kcp.io, so we'll look into that and we'll see. But we don't use CRDs at this moment for our internal operations, for installing stuff there, of course, for running Elastic clusters there, of course, but for the jobs we run there, we don't have CRDs because of the scale, the amount.
There's also a different one, so.
Do you run also Windows containers or just Linux? It's a good question. We haven't tried running Windows. It's all the nodes are in Linux, so we haven't tried Windows. I don't think it's possible to run a Windows container on a Linux machine. So no, it's just everything is Linux. Oh, there's one more.
Okay, just go on.
That's a good. Was that you? No. That's a good question. Do you move somehow your containers closer to the data source in cases data sources are in Singapore, in Amsterdam? Do you care? Okay. Yes, we do care about the speed of our customers. In some cases, we install the platform closer to the customer's data. So if it's a large client and he has a single tenant installation just for him, it is in that region, he has his resources and the express routes and all the networking stuff. So yes, we can move the whole platform closer to the data. We were also thinking about just moving the processing closer to the data, but it's a completely different story and a completely different talk. How do you know, and it's a really good question, I like this. How do you know how long is the job going to take to put them into groups? Yes, that's a good question. We know how long it took the last time, because the jobs, they do not change that often. It's a configuration that a user needs to run regularly. So he configures it, he runs it for the first time. We don't know what time it takes, so we put it in a bucket, not a random bucket, but a default bucket, the 1 to 15 minutes. And then we'll see. If it's longer than that, the next time it's scheduled, it's in the right bucket.
So you have a tag on them, or how do you know?
It's in our metadata. So we have we have history of all jobs, and we just detect it from there. And if it runs, then if it runs for 15 minutes 10 times, and then it runs for an hour, the next time we know, okay, the last time was 1 hour, so we are expecting this to run longer this time. So again, it's in the right bucket. It's super simple, but it works in that scale. It works. Oh, it's locked. I don't know if there's any other question. Have you tried pre-building VM call images with container image cache included? I'll repeat the question. It's a good question. Have you tried pre-building VM cloud images with container image cache included as pre-cached? We were thinking about it, but we have around 1,000, 1,200 images that are used every day, and we are not in full control of those images. They are built. They have the customer has a new version, so every time we would need to build that image. So it's not possible. It's too huge to pre-build that image. But for a single tenant customer that has a very limited number of images he wants to use, that could be a solution. Yes. It's a lot again, sorry. Oh, that's it. I'll answer from here. Oh, no, another question. How do you attribute network data transfers cost to customers? We do that, but very rarely. It's complicated. It's not easy. So we did that once or two times, and it was only looking at the destination because it was their database. So the traffic was from their jobs. So we were looking for some outliers in the network traffic, but we are not attributing transfer costs. How do you garbage collect images? It's a good question. Actually, we don't. Because the scale goes up and like the nodes scale up and down quite often. So they are destroyed, and they have a huge disk. They have, let's say for some customers, they have a 5 terabyte disk, and those images can be small, so it's not an issue at the moment. Even with that scale, the lifetime of the node is quite short to fill up with images.
Okay, now there's the space for the question in here. So
Thanks. So you said you don't use a customer resource, right?
No.
CRD. So you don't use a controller, your homemade controller. But
Yes.
how then you manage the life cycle? Do you have bash scripting or you have a delivery pipeline? Because I imagine at this scale, your unit of work inside Kubernetes, it's always a stateful set, right?
So there's a couple of services working on that single pod. So there's one service that is responsible for just putting the pod resource into Kubernetes, then it observes what it does. And there's another resource that once the pod is finished, it deletes that pod resource as fast as possible.
So it's your homemade service
Yes.
running, which manages the life cycle.
Yes.
Okay, perfect, thanks.
Yes.
any other question?
So the question is, it's probably you use Terraform for managing the stack across multiple cloud accounts. What do you use for managing Terraform? Or you use some kind of orchestrator, because it's probably not easy to write and support the code that actually can work across multiple cloud vendors. So probably you need something on top of it.
Yeah, we are currently exploring that. We have a pipeline that just deploys lots of Terraforms, and we are exploring how to move forward, because at 15 or 20 installations, it's somehow on the border of being able to manage that. Because sorry? I'm afraid to tell you. I'm scared. It's in Azure DevOps. It's in Azure DevOps, and we're thinking about moving somewhere else. Some of the pipelines are in GitHub Actions, but in Azure DevOps, we have some agents running in client's infrastructure. So the requirements for those pipelines are not super simple because of the networking stuff that happens in client's networks. So, but we are exploring Argo CD, I believe.
It's going to be deprecated, right?
Well, I think they say so for 5 years, but nothing happens.
So I think that's all. So if you have any other questions, so you can reach him.
I'll be on the bar.
Yeah, on the bar, or just during the networking part, or after this second talk. So, thank you.
Thank you very much.
We will have 10 minutes break, and then there will be the second speech. So, just take some refreshment and beer, of course. Please take your seats. We will start in half a minute.
Je to zelený.
So it's the time for the second speak. So please welcome Ondřej Smola.
So hello, my name is Ondřej Smola and I will be talking mainly about storage requirements and options for running your stateful workloads. Just a little bit intro. I work as a platform team lead at Newton Technologies. We are doing mostly like speak recognition, called AI these days. Also doing cloud consultancy for Harvario, it's IoT startup in Liberec, and teaching at Technical University of Liberec. What I really enjoy is cloud, Kubernetes, especially deep dives such as operators and controllers, and many CNCF projects. My favorite language is Go, and I like to deep dive into open source databases. My free time is basically allocated to family and my 3 kids. So goals of this talk, we will go through the storage types and requirements, some open source storage operators, and example stateful workloads we are running. And the goal of this talk is more of a like general overview than going deeply into specific topics. So coming from stateless workloads, basically before you had just CPU and memory, maybe some affinities, anti-affinities, and so on. And now you need to add storage. It seems like simple, yeah. When you have CPU, basically what you care about is like number of threads, or maybe architecture if you're running on ARM, for example, memory, just the size, and what can be problematic, storage, yeah. In start, it could look very simple. Basically, you can pick a size. If you have a default storage class, it will work out of the box. But the problem is that with the unless in memory and CPU, that it's a really deep topic, and there are a lot of dimensions. You need to get at least somewhat right, or you will need to, let's say, migrate your production data. So it's basically very hard to change later. So good to pick from start. What are the requirements? Yeah, to the images, I got a good idea that I will write the text and AI will generate the images, and it's somewhat mixed bag, I would call it. So for the requirements, their type, size, performance, redundancy, availability, encryption, cost, and many more. From the storage types, basically, you already know it's block storage. It can be local or network. You have object storage, usually called S3, sometimes blob storage, and shared file systems or shared files. So let's start with local storage. You already know like the spinning disks, but I would like to focus more on the like recent NVMe solid state drives. They have like really good low latency. You are somewhere between like 10 to 100 microseconds. For comparison, like the RAM is 1000 times faster. So, but it's really good. So you can see a lot of like solutions that have on flash at the end. That means that basically you can use the flash drives basically as a memory extension. What's interesting that for in many specs the writes are usually faster than reads. Why? Because the enterprise drives have like DRAM cache, and the writes goes to the cache and then it's like confirmed. The reads are slower, it needs directly to the disk, and the controller can like reorganize the writes and flush them. The size can be like up to many terabytes per drive, and you can have a lot of them per server. You can see the local storage is not about just like a physical machine you can run in cloud. It's like usually called like the, for example, Azure L series. Then you have like the drives also available as a storage. It has a very good per drive performance characteristics. You can do easily more than 1 million reads and 1000 writes per second, even with small write sizes, and you can sequentially read a lot of gigabytes per second. But you should beware, especially in, for example, some infrastructure as a service providers, that you can get consumer level drives. The problem with them is especially the fsync or the synchronized write. That basically means that the drive needs to make sure the data is actually on the drive and not somewhere in the cache on the way. And these drives, it's basically they have almost the same specs, but when you like do the writes synchronized, they fall apart, and you can basically be at the level of like enterprise spinning drives. Local storage, redundancy, as you might guess, if the drive fails, your data is gone. You can improve it, but you will never leave like the node level redundancy. You can RAID them, create a logical volume manager on top of it. They have a great cost performance ratio when you have the need for speed, or you are doing like a lot of, I will get to it like in the end, for example, analytical workloads, when you are scanning a lot of data. You can go really far with like creating a rate of local NVMe drives. You can have encryption. The great thing is consistent performance. It's really close to the metal. It's a very low overhead protocol. So you basically don't have many moving parts between your workload and your application. That means that you, when something breaks or didn't work as well, you have a lot less things to debug. What is bad about local storage, except the, like let's say, data redundancy, is that a lot of like cloud providers do like node replacements. So you need to watch out for your upgrade process, because you can get new node on basically, or new node on different machine, and the data won't be there. So your basically your rolling update or Kubernetes upgrade could end up without, you can end up without data. The next one is network storage. The sizes are usually, for example, in public clouds from like up to 64 terabytes. The great thing is that size can be increased. Yeah. When you buy like local drive, it's yours, but the size is fixed. The latency, there are basically two types of drives. The first is like sub in millisecond range and sub millisecond range. Yeah. For example, in Azure, it's premium SSD and new sub millisecond SSD v2. or Ultra and IO2 disks, for example, in Amazon. The throughput is like from megabytes to gigabytes. The IOPS you can get is more than 100,000 per second. But you can say now it's like almost as good as like the NVMe drive. But when you try to spec this, like it's really, really expensive. It can cost like the drive itself can cost like the rest of your infrastructure. The redundancy for the network storage, you can have zone local, especially the more performant ones are usually zone local. That means it's like in single availability zone. You can have multi-zone or geo-redundant. When you are moving from away of your like zone, you will always get increased latency. So it depends on the workload. The performance itself scales like can scale its size, like for Azure, for example, premium SSD, or can be decoupled. It's really useful for a lot of workloads when you don't need the size, but you need the IOPS or the throughput. You are usually limited by node size and type, and it's really problematic when you have like some workloads that are working okay, and then do some rescheduling, they end up on the same node. But you have like the limits on your volumes, and you have like total limit of the node. And then if they end up, they will be like throttled to match the max allowed node specification. You are also adding a lot of moving parts between. So your like network performance and plays a role, and it's really hard to. It's much harder to debug some performance issues. What is great about network storage is snapshots and incremental snapshots. That mean that you can create a point of time snapshot of your drive. It's really great when you, for example, upgrading database, you create a snapshot. You can, for example, when things break, you can recreate from snapshot, and it's usually much faster than doing like it from like object store. What you should be aware is like I call it standard storage. Yeah? A lot of providers will provide you with some storage. It can have some IOPS, it can have some throughput, but the devil is in the details. Yeah, because you don't have like guarantee about the latency. You don't know like what was the queue depth. That means that basically how many threads and how many instructions at time were given when you reach that number. And also the throughput, because when you, for example, don't have the information about the size of the IOP, which, for example, in AWS is basically 256 kilobytes, it's hard to measure. Also the bursting, yeah, they are problematic because when you start, for example, let's say database, the bursting will help you to get the data to the memory. But when you have, for example, some problem and the pod restarts, you will run out of your burst credits, and now you will find out that your actual IOPS are much less, and it's problematic for your production. Also, you need to be aware of the zone local storage when you are starting or deploying your workloads, because you need to make sure that these drives, for example, when you are deploying across 3 availability zones, end up each in 1 availability zone, because you cannot move them easily, and your pods won't be able to connect to mount these volumes. Also, it can get very expensive as performance increase, especially in public clouds. But what does it not replace is application level redundancy. Yeah, you always need, if you are caring like about high availability, the redundancy on the storage layer and also on the application layer. So, for example, databases, you need multiple replicas. Object storage, basically the size is unlimited until you hit your account limits. The latency is somewhat between 10 milliseconds, it's like the newer one, such as AWS Express Route, to 100 milliseconds. As for the latency, also for the Express Route, it's now zone local. Yeah, that means it's not available across availability zones, so you can get better performance, better latency, and it's using high overhead protocol. The throughput, it depends, but you can get somewhere between 10 to 100 megabytes per object. Concurrency is basically limited by your rate limit and network bandwidth. It has a lot of cool features such as hook and policy, so you can do some actions. For example, move the object from different storage tiers after some time. The storage tiers basically what they do is they change the price between the storage and operations, and in some cases the latency. It's priced basically usually on data stored. The great thing about it is that it can go down, because when you provision like the block storage, you usually cannot go down. And also you can be built by network transfer. Yeah, there is like the zone geo-redundancy. That means, for example, that as I already told, the express one is zone local. So let's move on and look what can we do when we are not in the public cloud. We have, for example, just a bunch of machines and we need to have some storage. You have the simple ones. They are simple, but the problem with them is they are extremely limited. You may already know like the mddir. It serves as a cache. It's there. It's on the host. It's there as long as the pod is the same. It means that it survives the restart, but when you change the specification, for example, of the deployment, it will be gone. Then is host path. It's great for security because you can mount to host file system, and there are local persistent volumes. The problem with them is that they need to be fixed to node, so not really great for like more dynamic Kubernetes clusters, and the paths must be created. You can like work around it, but it's not very, let's say, pretty. There is a local path provisioner. You can know it if you are using, for example, K3s or micro Kubernetes, where it is as an add-on. What does it do is it provides storage as a dynamic subdirectory on local node, but it has a great problem, and it is that it doesn't enforce capacity. And as you may guess, it's a really big problem because, for example, you specify that you need 5 gigabytes, but it's not enforced. So one of your workload could easily like kill the node basically by filling all the available disk space. You can like somewhat mitigate it by giving it different drive, but in this when you have like this type of deployments, usually have the only drive is your like system drive. The much better solution which we actually use is Topo LVM. I think it's less known, but very great project, and it uses node local LVM volume group to provision storage. So you basically have your nodes, you have local NVMe drives, you can create a RAID, you put a LVM on top of it, and you create a volume group, and this volume group will be detected by the Topo LVM, and it will provide it as a storage. It has a great feature, it is capacity aware, and it enforces capacity. What does it mean? Is that it knows what's the free space on every node, so it tries to be intelligent to not schedule all your workloads on the first node in the list. It supports volume expansion. You are always limited by the node size, yeah, because it's like node local storage. It's topology aware, so basically you can do like the failure domain setup. It supports firm provisioning. The difference between thick and firm provisioning is that the thick you need 100 gigabytes. It will allocate 100 gigabytes, and it's yours. The firm provisioning is like it will allocate the minimum and it will grow as you need. The great thing about the firm provisioning is it supports snapshots, basically local. They are local, so not good for your backup, but really great if you need, for example, to test database upgrade or like some component upgrades, because as these snapshots are local, their recovery time is almost instant, basically. It has a lot of Prometheus metrics and so on, and it can be deployed by Helm chart. The next one, let's say much more popular, is Rook and Ceph. What does Rook does is it's an operator for managing Ceph clusters inside Kubernetes using custom resource definitions. It's very, let's say, it has a lot of features. It can handle upgrades, it automatically detects drives, it's self-healing, and much more. What is Ceph? it's a distributed storage provider. It's very mature and battle tested. It's a storage provider for a lot of solutions from like some public clouds to OpenShift CERN. What does it provide is, and what's great about it is basically provides everything in the like network storage space, from block storage to scalable shared file system to object storage. So basically, when you have Ceph, you can do in one, like using one system, you can provide all of these. Just a little bit deep of the architecture. What does it do? Is basically turn your local drives. You can, it's these OSDs button, then run some services on top of it, and these provide all these like storage types. The great thing is it's like unified, and it has a like data placement logic that can basically that turns your storage into some objects. The objects are, let's say, from around megabyte to 4 megabytes, and then they are run through pool that replicates them and stores them into placement groups that are mapped to OSDs. That means that you can have volumes that are much bigger than your local disks by itself. Also, like by distributing this, you can get a very good throughput. It supports failure domain, so you can tell it that, for example, these are like free racks, and you want to have every copy in different rack. It's much more optimized for overall throughput-oriented workloads. That means, like, for example, analytical workloads, than like single client performance. So larger transactional databases are usually not a good idea. And for example, running consensus protocols such as etcd, Zookeeper are usually a very bad idea. The great thing is it's viable even for small clusters, such as you have like 3 nodes, small nodes, and you need to create some redundant storage on top of it. There is a project called Microceph. The problem with like the single client performance tries to be solved by the next gen OSD type. That's the like the storage type. It's called Crimson, and it's using much low-level and optimized protocols that take account into the like new generation of NVMe drives and storage network. So you can not match, but can very close to what you can get with a local NVMe drive. In the last section, I will go through like some stateful workloads we are running on Kubernetes and how we are like managing them. For Postgre, we are using, and I highly recommend open source cloud native PG operator. That's basically came from like Enterprise DB. I call it my own RDS. Our deployment is basically free zone redundant replicas. In our case, it's that free data centers with quorum sync replication. What does it mean? It's basically that we have free replicas, and at least majority, so 2 in this case, needs to the write needs to go through 2 of them, and the third one is async. I really recommend having like wall and data on separate volume claims because you need to prevent when you like run out of storage when nobody is on call. So basically, you will also like go through your wall storage, and you cannot like close clearly, and you may lose data. It has embedded options for wall archiving and backup to external object storage, and all this is like automated. The operator handles master failover, application level replication, scaling, rolling updates. It has a kube control plugin, Grafana dashboards, and alerts. Yeah. For the storage, to match it with what I talked about in previous, transactional workloads usually like smaller mixed I/O. That means it depends on your workload, but it's usually smaller and it's latency sensitive. So you should prefer like volumes that can deliver higher number of IOPS and consistent latency. Ideal if you can get like with these like premium SSDs V2 under 1 millisecond, and you should have like 1 copy per zone. There is a great project called CNP Bench that you can use. There is a lot of instruction how can you like benchmark your storage. For the backup, it supports wall archiving for point-in-time recovery to object store, and for data, you can have backup to object store. It's basically the full backup shipped to object store, but it also supports volume snapshots even in clouds. So it's really great, for example, during the upgrade. And even you can have both. So you have periodic volume snapshots. They can be incremental if your platform supports it, and you can have like once a week full backup also shipped to object storage. We even run this on like on-prem when we have like local storage, because when you think about it, if you have like the local drives in RAID and you have 3 of them, they are separated, you have like backups to object store, a lot bad things need to happen, so you lose your data. And you get a very great performance on top of it. The second workload is ClickHouse. Like the Postgre, I think everyone heard of. The ClickHouse, it's popular open source analytical database. It's basically columnar store for real-time analytics with SQL support. It's not like in comparison to Postgre, it has a lower concurrency, but it's focused on compression, storage policies. So basically can have, for example, some storage on fast NVMe drives, some part of like local spinning drives, and the third part on object storage. Our use cases, we record per request metrics and we use them for alerts. Basically, for example, time to first output, start time of the speech recognition engine, cache hit, speed. We use it mainly heavy to compare different versions. Yeah, because for example, somebody creates new model, we deploy it to production, and we need to make sure that the new model is it may be better, but it's much slower. And a lot of clients care about like the guaranteed response time, so we need to monitor, and it's a lot of data. So basically, running it into ClickHouse, we need to like go from the Postgre to ClickHouse to make it work. And also the machine learning, the speech recognition engine emits a lot of events about like the inner workings. So we store them in ClickHouse also. We run it as also by operator. This time it's a ClickHouse open source ClickHouse operator from Altinity. The ClickHouse itself is like 2 parts. It's server, which stores the data, and then there is a keeper. It's same as like etcd or Zookeeper. It's the metadata store. The storage for ClickHouse, your target is different. It really likes large, or its goal is to do large sequential scans of compressed columns. So you basically need to throw as much throughput as you can on it to be like performant. So block storage on Ceph, really great for this. Like a lot of big deployments, such as in, for example, Cloudflare or PostHawk, uses basically local storage. Also, you can use it in some mixed object storage and local cache setup. The backups are basically as object store. You can do, it has support for incremental backups. The keep requirements are different, but they match the etcd I'm going to talk about next. You may heard of it. It's distributed, strongly consistent key value store. All data is basically in memory. It's running something called RAF protocol. Our usage, and basically your usage usually, it's like the storage for the Kubernetes control plane. We also use it in different workloads, such as like the scheduler agent coordination, and we deploy it easily by stateful set, because we don't need, as it's like in memory, you only thing you usually tune is like the memory and CPU. Yeah, the storage is basically fixed, and you usually know there are free replicas. So, and for like when we are bootstrapping our Kubernetes clusters, it's run like on the control plane. For the storage, etcd is really latency sensitive. If you have like big commit latency spikes, it can cause like member disconnect, and if this member is your leader, it's not good ideal situation. You should prefer local SSDs or very consistent network storage. Yeah, you are caring not much about like the IOPS, as you can see. Even for 1,000 node Kubernetes cluster, the recommended performance is not like something you cannot get easily, but you really need to take care about the latency and the spikes. For this, you can use the built-in tool called etcd-checkperf that has like switch. You can select how big your cluster be. You can use it not just to simulate your size of your cluster, but your workloads. And for backup, basically, what we do is we do periodic snapshot and ship it to object storage. And the last slide, basically, you may heard of the term storage compute separation, and in combination, what it does is like combine all these storages for their like advantages or strong sides. So you usually have some combination of object storage. That's then you have like fast local caches, and your metadata stores are usually on fast network storage. And that's basically it. So if you have any questions.
So as we still don't have any question on Slido, so maybe we can try some here. Okay.
So maybe a question, if you could maybe share some experience with the local storages. So do you with the node local storage? So do you have any I don't know, experience with getting the data out of the node if you need to, I don't know, decommission it, remove it once you are basically done there?
If we speak about the applications itself, for example, the Postgre, the operator itself can handle it. The Cloud Native PG even supports like change of the storage class. So basically, when you are on bare metal, one of your nodes are down, you can like create you will need to like replace it, and the operator itself will handle the like recover from the last base backup and do the like synchronization. It has a great like Grafana dashboard and CLI tool. You can watch it real time. We didn't have a lot of like complete node failures because we use RAID, and usually it happens so that only one drive fails. But we did the like the node movement part because we somehow didn't get it right first time on the node size.
So that's basically application-specific solutions for that.
When you are talking more about the Ceph or
No, the node local storage. So how do you get out the data out of there? If you need to like delete the node, get rid of the hardware. So PostgreSQL, sure, you can replicate it somewhere else. Is there something on the block level that you could use? Maybe one of the operators or the CSI providers that was that you mentioned for the local store. Whether they can
I'm
do
sorry,
like
I'm not sure I understand this.
okay, sorry. Let's talk later.
Yeah. Sorry.
Any other question? No. So maybe I have one. So, have you ever?
Yeah, there is one about everyone knows some funny Postgres story about lost data. What about ClickHouse? How do you like the maintenance of ClickHouse cluster? It's not yet so popular. Yeah, but what's great about the operator of Alternity is actually they like the goal is to run the same operator in their like their SaaS, and they open source it. So even it's not used very much in the open, it's actually really battle tested. You need to get some things right. For example, the storage management, because you can have like a stateful set based storage management or external. Yeah, that means that the operator itself allocates the storage and attaches it to node, or you like it just creates like, for example, free stateful set, and each stateful set storage is allocated by Kubernetes. If you get this right, what's the problem? The problem is that if you do the stateful set part and then you resize it, the problem is that the size in the stateful set is immutable, and when the operator detects it, it will try to recreate the volume. So basically, recreate the stateful set. So it's like need to. But the backup itself, our goal is we rely a lot on compression. My main motto is to keep the data as small as possible, even for the OLAP, because when you get like to the terabyte sizes, the problem is that our on-prem networks are not that great as you are in public cloud, and streaming like terabytes on some small, let's say, less than 10 gigabyte network, it takes some time, and you cannot like recover in time basically. So we usually like split it or do some tiered storage. Yeah. If it's like the answer. But we haven't lost ClickHouse data yet. I haven't looked at the phone, but still no.
Okay, so I have also a question. So, have you ever tried any, hardware solution, like for example, from the pure storage? I mean, for
No.
the storage ones?
No, we haven't, because let's say for a lot of workloads we are basically on IaaS or on-prem, and we need to work in some environments that we'll need to rely basically on the hard drives and network. Yeah, and as my motto is, as less moving parts, the better. Yeah.
Thanks. Next question.
So just to confirm, so for the databases you use local storage with the RAID under the hood, and for things like ClickHouse, or what's the typical split? When do you choose Ceph, and when do you go with local storage?
Yeah, we have one deployments on bare metal, and then we have in Azure. In Azure we use we don't use local storage, we use network drives, and for the on-prem we use local NVMe drives. And why don't we use Ceph? Because it's also for the Ceph you need great network, and we don't have that. Yeah, because if you don't have the great network and something breaks, the data replication will basically it will go down painfully. Let's say.
Yeah, I can agree. If you have no experience with node crash,
so for the Ceph,
in Ceph, I mean.
For the Ceph, it's a great tool. We used it. We basically now don't use it. It's great, but it's a lot of a lot of knowledge you need to have, and a lot of you need to get it right, as in storage. Yeah, if you made a mistake, it will work till it won't, and then it's late to. So basically, if you don't have the hard requirements, it's usually better to rely on provided solution, of course. Yeah. For the local drives, you can rely on the the protocol and the kernel. It works. But going from local storage to network storage, definitely, if you don't want, it's better to have managed by somebody who knows who's doing with it.
So last chance. So any other question? If not, so thank you, Ondra. So for the live stream, it just ended, but for the guys here, so it's not ended. So we have at least 2 hours for the networking. So don't go away and just take some beer, so we can talk about it.